Before I jump to my talk, I'd like to quickly introduce my colleague, Scott. He is the FCC expert. He is having a very versatile background. He will also talk about that. He is in charge of the FCC R&D group. He's having a lot of initiatives going on with improvements in the hardware features, process, decarbonization, energy transition in FCC. So he will take over half of the talk. After 15 minutes, we have a deal that I'll have to hand over to him. And so the second half is going to be covered by Scott. Before I start my talk, another thing to share this our journey with Barracuda. I think we started using Barracuda in 2009, I believe. And I think Peter or Sam, I don't remember right now, but I think one of you guys have trained us at that time. So that's where we started. I've seen the transition of the improvements in Barracuda. At the first, we can't even specify the particles, the rate of the particles feed. We have to specify all parameters, slip, velocity, and other things so that we can check whether we have the particle flow or not. But over the course of time, it has improved a lot, and it has done a marvelous job in coming up where it stands right now. To start with the talk, I will briefly touch base on the technology features in FCC we offer. That will set the background of the talk, and then I will be discussing out of 5 modeling success examples. I will do 3, and Scott will cover the last 2. Basically, these are the case studies or applications of Barracuda modeling where we have used, and it end up to industrial applications. So it will correlate where we are, how we get into those ones, and what type of success we got out of that. And last, we have a modeling challenge example. Not everything we can model. So I will discuss one of the one of the case also where we are facing a lot of challenge to model it. And maybe it will open up a brainstorming session with you guys to see whether what else can be done in that regard. And finally, the summary. So start with the technology features. So this is how our FCC looks like. It's a 2-stage regeneration with the reactor. There are a lot of proprietary components in that. The riser termination device, we call it RSS, riser separation system, the stripper packing, the baffles in the stripper section, the feed nozzle, air grid, the spent cat distributor, the Y bar tub distributor, which we put it in a first stage or in a single stage, and a mushroom type distributor, which we have in a second stage of the regenerator, and a cat cooler bundle, which is our modeling challenge, basically. So apart from the air ring, I think we have used Barracuda in all different features to see what type of improvements we can make when we make the hardware changes, what should be the impact, and whether that impact is going in the right direction or not. So I will be discussing these in the follow-up examples. But a quick note on the FCC, it's a fluidized bed. You have a feed over here in the form of the oil droplets. The hot catalyst comes over here from the standpipe. It flows along the riser, cracks over there. The vapors and the catalyst is going to separate in the riser termination device. Catalyst goes down, flows down through the stripper packing. The baffles, steam is going to strip the hydrocarbons, and the vapor is going to go up, and to the main fractionators, catalyst flows down. In the regenerator, as a byproduct, coke is going to deposit on the catalyst. So we burn some of the coke in the first stage, then move the catalyst to the second stage, burn it over there. If there is coke is too much, we have a cat cooler design to remove the heat out of that. So simple design, fluidized bed, kind of a pneumatic flow in the riser. We have a downflow in the stripper section, turbulent bed in the regenerator 1 and the regenerator 2. So yeah, it's a whole circulating fluidized bed. Moving to the next example, the first one, the improved catalyst retention with optimized RSK design. And this slide basically shows our evolution of the riser termination device. Right from 1980s, we started from uncoupled RTD systems, ballistic separators, stair horn, different versions of the RTD. And then we moved to RSK, which is a close coupled with cyclone design, We have a first generation design 20 years back. We did a lot of testing in late 90s, where we did a cold flow test, we did modeling, not with Barracuda at that time, but we did modeling, we got with the design, we have implemented in almost like 30 different applications, and out of which almost 60% are EVAMs. We got reduction in the dry gas from 8 to 18%. Catalyst retention is pretty good. But now we are also looking at the next generation of RS care, because there's always room to improve, always room to see what next we can do. And we are having a next generation, next campaign going on with our alliance partner, IFP, where we do a lot of testing. And before we get into the testing phase, we have done Technip, IFP, Exxons, we all have done a lot of modeling with Barracuda to see what different changes we can make to improve it further, to make it more compact, to make it more compact so that we can preserve the oleficity of the products, and we can improve further the catalyst retention out of that. And during the course of time, we tested different configurations, and we found that one of the second generation, I'm calling it, because we moved from our standard offering was earlier two-chamber design. From two-chamber design, we went to a four-chamber design, and we looked at it, and it found to be, from the CFD, found that, okay, it looks like the efficiency is going to improve quite a lot. So we looked at the different angles, the flow, velocity profiles, and some quantitative comparison of the efficiencies, whether how much it can give in terms of the delta improvements. It looks pretty good. It's more symmetrical, more compact. So in one of the applications, we decided to install it. It is a low risk proposition for us. So we installed in one of the unit, but before installing it, we looked at with more depth. It's not just the process performance. We also look at the mechanical reliability, the erosion pattern, because generally these RTDs doesn't need any maintenance for multiple turnarounds, which means like 10 years, 15 years. But are we making any, by looking at the performance, are we jeopardizing the mechanical reliability? So we looked at the erosion patterns. It looks like the velocity profiles are a lot more uniform when we go from a bigger chamber size to a smaller ones. It's just an analogy of cyclones. When you have two big cyclones or four small cyclones are generally more efficient. So that similar concept over here with this RTD. From a two-chamber design, we went to a four-chamber design, more symmetrical, more even. And then we implemented in December 2022. So this study was done almost like 8 years back. And I was talking to Reza, I said, oh, you're showing this stuff, CFD simulation. So are you doing CFD anymore? Not much. But it's a journey. Like yesterday, Peter and Robert was mentioning, it took 9 years. In FCC, it always takes, turnaround is going to come in 5 years. So it was implemented in one of the turnaround in December 2022. They are operating for almost like a year now. It runs smoothly, no surprises. Actually, they got a lot more, a lot higher catalyst retention. Here I'm showing this slurry BSMW from pre versus the post turnaround, almost constant. There are some hiccups during the startups, which always happen. They were having a couple of startups after the post turnaround, but they are almost stabilized, no more surprises. And the revamp was done for a higher severity operation to maximize the propylene. Higher severity comes with a higher riser velocity, higher cat circulation, higher conversion, lower slurry yield. So lower slurry yield, which means that the BSMW, the ash concentration is higher, but slurry yield is lower, so which means that my catalyst collection efficiency is much higher, in spite of the fact that the concentration is more. So it is running pretty smoothly. Client is happy, we are happy. So this is our second generation. So before we move to a third generation, which we're already having a campaign going on. So this is one of the good example of modeling, testing, and real application of it. I will move to the second one. No, before move to the second one. So there's always a concern in the CFD. Are we capturing enough details in the model? Or in the earlier models, we did the section around the RSKR, limited boundary. So it's always computation intensive. And here I'm showing one of the examples where we did model the whole reactor. It has riser flow inside. It has the riser separation system, even the flow in the cyclones, and even in the plenum. So the boundaries were done all the way out, so that there will not be any impact of any boundary condition on the hydrodynamic prediction of the or prediction of the hydrodynamics. And pretty big model, 8 million cells. Particle count is low because the bed is already covering over in this section. So it's 8 million particles, 8 million cell count. Took us a long time to run this. We run multiple cases. Probably in this one we have run almost 20 to 30 different cases. It runs smooth. Results are similar, but it found a lot more stable in terms of the hydrodynamics. So our smaller domain and the larger domain, we do like to check over the course of time to see whether we are covering enough details or not. So this is one of the examples where we find that, okay, it was interesting to capture all the details. Cyclones flow, it has almost like, I think, 22 cyclones, something like that, and that was also captured in the model. Now moving to the second example. Here, as Joe was mentioning, the different versions of the SpenCat distributor. So this shows our journey of the SpenCat distributor from, again, 1980s. We started with a hockey stick with a slotted opening at the bottom. Then we have the bathtub, then single arm bathtub, then we moved to a Y bathtub. Then from there we moved to a compound angle so that we can maintain the flow, the momentum in the first section, and then to slow down from compound angle we move to a, again, Y or a single arm, but submerged bathtub. So it all depends upon the feedback we got from the industry. As the FCC units becomes bigger and bigger, the regenerators becomes bigger and bigger, where I'm showing over here in terms of the diameter. The temperature, there is a temperature variation from one side of the vessel to the other side, where we call it in a dense phase, there are 4 thermocouples. One side was showing where we are dumping the catalysis, dumping the spent catalysis having a lower temperature versus the other one. So this delta goes pretty high. So with these improvements or changes in the design, which was modeled, we have lowered that temperature variance in the bed and the afterburn in the vessel. And here I'm showing one of the example. This unit was this design was implemented in Suncor Edmonton. The paper is also published, where we changed the existing distributor, SpenCat distributor with a single arm, because there's a small regenerator submerged in the bed, in the catalyst bed. Gives a lot better distribution. The temperature variance in the dense bed and dilute bed both goes down. Afterburn goes down. So it was a successful implementation. We already have 2 more, including this one, 3 total installations of this type of distributor in the industry right now. Moving to the third example. Here we are showing the journey of a gas solid distributor, which we are using, a mushroom type distributor in the reactor and in the second stage regenerator. The purpose is to distribute both the gas and the catalyst coming in from the reactor or from the riser or in the lift line, which we use over here in the catalyst bed. So we moved from a simple bird cage to a mushroom distributor. Then we added some features, the skirts at the ends or sides. So mainly to improve the coverage of the catalyst in the bed. What we found from the initial modeling that the flow is basically, the flow coming out of the lift line or the riser is concentrated in the center only. But our initial thought we have was that, okay, are we modeling it correctly? Or what we are seeing, is it a real thing? So we did the testing at IFP, where they also found that based upon the helium profile, there is higher concentration in the center, which proves that what we are modeling is kind of a real thing, what we are seeing. So based upon that, we had number of ideas, we modeled it, but not tested it, but modeled it. So, and then we come up with a final design of mushroom with the branch arms to spread the vapors all across the vessel. And call it quantitatively, it looks like the gas flow uniformity, it increased by almost double. Reaction, the conversion, it increased by almost by 60%. So that was in the reactor application. So now we're looking at how we can apply to the regenerator application. In the reactor application, the riser was having almost like 90% of the flow. Here, 90 to 95% of the flow. Here, we only have a part of that. So here I'm showing two configurations. Industrial scale regenerator, second stage regenerator, we use that. This was the existing one, and here we are trying to do changes in that existing one. We lowered the rings, put a new, raised the mushroom, put a new branch arm mushroom over here to see whether how does it, what the results will look like in terms of the afterburn, coke burn, temperature profiles, other flue gas analysis. So some of the results, it shows over here again that the vapors are concentrated in the center. They show a lot better coverage, lot in terms of gas flow uniformity. It improved. The density profile looks good. It looks a lot more promising compared to the earlier design. Here we're looking at the temperature profile. As Scott was mentioning earlier, sometimes I think in this model, what we are seeing is that we're not seeing a reduction in the afterburn, but we do see increased carbon burnout rate or more efficient use of air to burn the carbon. So we may need to adjust the carbon which is coming in or on the existing particles to match the carbon burnout rate, but definitely there is an improvement in the combustion of or the coke burnout rate or which is the result of the improved coverage. We also looked at the CO profile in the existing one, which is pretty high in the center. By using the optimized design, we reduced that. The catalyst which is coming from the lift line, a lot more distributed compared to the existing design with this new distributor, and even the coke carbon concentration, which show a lot more mixing compared with the existing one. So now I will hand off the rest of the presentation to Scott.
Thank you, Raj. Appreciate the introduction. Just a couple of other quick examples. So we're kind of talking about FCC and different iterations of it. One of the versions of FCC is our high severity FCC that we license. Also, Axon's licensed this technology. Originally developed at King Fahd University with Nippon Oil and Saudi Aramco. But this is unique because instead of a riser, it uses a downflow reactor system. And the main difference is that in a riser, you have a lot of back mixing. So you inject a feed, it's all getting mixed and swirling around. Here, the feed zone is very important because as you travel down the downflow reactor, there really isn't any radial mixing. So that first portion of injection is very critical. And so we did a little modeling, injecting as a vapor, the feed as a vapor, and there's a lot of internal debate on whether we're really capturing everything. So we approached CPFD, and they did some modeling with this VLS feature. I think it was a beta feature at the time. We're injecting particles of liquid feed. So we can look at the catalyst and feed mixing in that zone and try to improve the performance of one of the commercial units. So this is a little bit about the model. Basically have the catalyst flow boundary coming in. There's 6 injectors around the circumference. There's feed being injected through the feed nozzles. There's multiple discrete points for each feed nozzle, kind of spread out in a fan pattern. And basically from cold flow modeling of our feed injectors, we know the droplet size distribution, We know the volume flux distribution, the spray angle. So we can kind of simulate all of those aspects of the feed nozzles and try to simulate what's happening in this section. Steam is just injected as point injection boundaries because it's not as critical as the dispersion of the feed. And then basically we've got just simple pressure BC at the outlet here. You can kind of see on the right, basically a plan view of kind of how the droplets are being sprayed into the downflow reactor. Oops. So base case simulation was run. You're going to see particle volume fraction here and also fluid temperature. One of the things you notice right away is you get a lot of catalyst bypassing the feed, so there's not perfect mixing and really good interaction. You've got catalyst bypassing between the feed nozzles. You got a central core of catalyst in the center because the feed is not penetrating to the center. So you can easily see that in the particle volume fraction. Also in the fluid temperature, you see a very hot zone in the center, and then a little bit also along the walls. So using this modeling is really helpful in kind of identifying some potential phenomenon that's going on in the feed mixing zone. And of course, as you travel down the downflow reactor, you see very little lateral mixing. You get one shot at it at the beginning to get it right. If you don't get it right, you're stuck with it. So we simulated some modifications. So the modifications were basically, okay, let's put baffle above the feed nozzles, kind of block all the section between the nozzles. Enlarge the plug so the feed didn't have to penetrate as far to the center. And then put one mixing baffle at the bottom, kind of kick out the catalyst from the walls and give it one chance to mix before traveling down to the fully developed zone. And you can see on the right, particle volume fraction and fluid temperature comparison between optimized case and original case. Things you can notice are, the central core of catalyst is still there, but it's definitely broken up a lot more than the base case. And you can also see in the fluid temperature, it's just a lot more homogeneous fluid temperature across the downflow reactor than the base case. One of the things, though, about the VLS is that it really gives you another metric to look at. This is what I like the most. You can really see the improvement here by looking at the feed droplet resonance time and also the liquid fraction of the particles as you travel down the downflow reactor. So you can see droplets hang around a lot longer. In the original one, we're not vaporizing everything as quickly in optimized design. There's very few droplets that make it further down the downflow reactor. And liquid fraction is just kind of another way of looking at basically the same phenomena. And you can really visualize the difference between the two cases. So this was really nice. We worked with CPFD. They modeled this. The model helped us assess different designs. It was implemented in the commercial unit, and of course they immediately got increased conversion, higher olefin yields, lower dry gas, lower slurry. Very successful project, and ultimately, there's a patent granted for this design, so you can read about it more if you're interested. So after working with CPFD on that, I thought, well, why don't we try the same thing in a riser? Let's set up the riser model and try to use the same VLS feature. So I set up this riser model for another commercial scale FCC unit with 60,000 barrels a day. So the model, you've got your flow BC hot catalyst coming in. You've got the injectors. There's 8 injectors around the circumference. We arranged the feed nozzles in the same similar spray pattern, and again, pressure BC at the outlet. And here's what happens when you do a riser. So you've got particle temperature on the left, liquid vapor fraction in the center, and then particle resonance time on the right side. And so you kind of have to wait about 20 seconds into the simulation. I delayed the feed injection because if you start it right away, the bottom just fills up with liquid particles, and model didn't really like that too much. But you can see after about 20 seconds, the feed's injected. Kind of cool illustration of the spray and the feeds coming in. One of the things that we looked at was, well, how fast are the droplets really vaporizing? And there's an interesting paper that kind of is a compilation of different feed vaporization models. And one of the things that we saw, I guess this compares different models for a 300 micron droplet size. Of course, we don't have 300 micron droplet size, we've got a distribution, but it's pretty close to the solder mean, let's say, for the feed nozzles. But you can see, probably about the light blue to green, droplets are really disappearing. So if you say somewhere between 50, 150 milliseconds, most of the droplets are disappeared. Probably the big ones are still hanging around, but they're very few. So it's a really interesting metric that we can use. So that's one of the things we're doing, using this is just a comparison of, say, if we inject a feed at two different velocities, what's going to happen in the riser. You can see on the right side, we're looking at the average feed vapor fraction across the cross sections of the riser. And then quantitatively, we can actually calculate, this is cumulative liquid droplet mass passing through a flex plane. You can see for the high velocity injection, there's a lot less liquid crossing that flex plane, which means you are doing much better job vaporizing the feed. So this is an interesting tool that we can now use. We're exploring it in different R&D programs that we got going on to always improve this section of the FCC. And just kind of want to share that with everyone. So go back to Raj for the last portion.
The last one is the modeling challenge, what we are facing. Mainly, it's a commercial scale catalyst cooler, which has almost which has 32 clusters, 6 tubes, each cluster, 200 tubes almost, and difficult to model. Lot of walls, and very computation intensive. We're using 7 million cells, 32 million particles, because that was our hardware limitation also. It's already reaching 30 GB RAM of GV100 card. It doesn't show the profile which generally exists in the catalyst cooler. We have a data for that. It shows pretty dilute section in this side. Over there, we use different drag lows. We have used the baffle feature also. It was interesting to use the baffle feature because when we use the baffle feature, baffles are kind of hollow, so we have to make sure that we are initializing it correctly. But a lot of the time, either the gas flows through the baffle and not to the bed, because now baffles are empty, because gas is going to go to the least resistance path. So we filled the baffle with the initialized with the like a zero flow or zero flow the particles over there, filled it, but we didn't get any success. We almost spent like 6 to 9 months, and where is Sam? Sam was part of that. Done number of simulations on that. Resolution in terms of it's a 2-inch gap between the tubes, 2.5 inch, 10-foot wide. In terms of the height, it's pretty long. But yes, it is very computation intensive. There were other challenges also we had. It's a downflow system. So we had a standpipe section also to first simulate the standpipe correctly, and then simulate the bed, and then simulate all these walls. It was kind of computation intensive. So yes, we are, I think in Barracuda, the walls are kind of frictionless. So there is lot of flow along the walls, which shouldn't be there. It happen, but it do exist that to show that. But this is kind of a challenge we have right now, how we can model this. This is the start, the hydrodynamics. Once the hydrodynamics will be there, we have to model the heat transfer. Once we have the heat transfer will be there, then we will see, okay, then the objective is to see whether to study the impact of the pitch or the tube clearances or tube gaps on the heat transfer, on the duty of steam production. So it's a bigger, our intent is quite big to capture the whole thing, but we are stuck with the hydrodynamics right now. Yeah. Any thoughts we can share after our talk? And the next one, just to summarize, yes, we are actively using CFD. In our group, we use Barracuda mainly to model because we are gas solid, and Barracuda is right now is one of the best tools to model, to use that. And we are improving designs, continuously using this tool to look at what features we can improve further. We are developing new IPs based upon that. There are a number of patents we have filed using the results and real applications. It helps us to screen the new concepts, the testing which we're doing at IIT or other places also. We screen those beforehand because we cannot spend too much on testing all the different ideas. So we use this tool. The VLS feature, as Scott has mentioned, it is helping us to improve further designs in the riser application, in coming up with new process schemes also, which we are testing in terms of the conversions and reduction in the dry gas or other features of the other features in the reactor applications. So yes, we have successfully used it in many different applications, commercial applications, and got good results. Thank you.